2 days ago, we have launched a new product. It's called the DJI Zenmuse L3, and very exciting product there. And so today, I'm gonna for the next 2 hours, I'm gonna go through this product a little bit in depth, talk about the capability of this system, and talk about some use cases. And along with this new product, we have released a few updates with our drone and softwares, which I also like to go through those as well. Now, I also have my colleague, Grant and Michael, on board as well. So if you have any questions, please feel free to ask in the questions section, and Grant and Michael would help address any questions you may have. Now let's get started, talk about the L3 system. Very exciting product here. But before we deep dive into L3, let's talk about the history of the DJI Zenmuse LiDAR series. First of all, we have released L1 back in 2020. So that is about 5 years ago. This is our first highly integrated airborne LiDAR system. And some advantages back then when we first released the product was following. First of all, it is a LiDAR sensor with a gimbal system. So that means you can manipulate the viewing angle however you want, just like other Zenmuse gimbal payload we have. And it's also a LiDAR combined with a photogrammetry RGB camera with a very friendly price tag under 12K euro. And it has a one single port installation, so it communicates directly with our drone platform that doesn't need to attach individual battery for powering the system, nor individual IMU. It is highly integrated. And we also provide one software process for getting the results outputted in LAS, that is our Terra software. And back in the time, we have released the real-time point cloud processing feature. You can view the point cloud in live as they're accumulating, as they get accumulated during the operation. So make sure you have covered the site without missing a spot. So these functionalities available, makes the L1 system extremely efficient and easy to use. Back in the time, the particle or practical measuring range for the L1 was 80 to 100 meters, with a typical accuracy of 6 to 10 centimeter in vertical. And of course, after that, we didn't stop from there. We have released L2 about 3 years later. And it's a significant improvement from the L1 system. Supports 5 returns and increased the range to 450 meters practical range. And it does not require IMU preheating, just like the L1. If you had experience with L1, that was a process you have to wait, but no longer for the L2. And for the L2, we have made the decision to have user to use Terra for free to get the LAS data out. And it supports PPK process within the Terra software, so you don't actually have to use RTK. And we have improved the accuracy to 4 to 5 centimeters for typical measuring range at 120 meters to 180 meters. Now, we're very excited this week to announce L3, which is another great leap from the L2. Now supporting 16 returns, 950 meters in range, and dual 100 megapixel visual cameras. Also supports fusion Gaussian splatting functionality. And now not only you can view the points clouds being accumulated during the operation, you can also manipulate the results directly from the remote controller and do quick measurements on the controller side. Now we have increased the operation and measurement range thanks to the L3 and the M400 system to 300 to 500 meters for typical or practical measurement range, and have increased the accuracy from to 2 to 4 centimeters. Now let's talk about these individual functionalities and updates in detail. First, let's break through the system. Updates contains following: high energy laser, high precision IMU, high resolution dual camera system, and overall highly integrated manufacturing. We're able to put this highly integrated system in a form factor that is extremely compact but mighty. So let's have a look. First of all, we have a high energy laser, and we have implemented a greatly improved IMU module, and we also have included the high resolution visual cameras. These cameras are designed not only for colorization, but also for photogrammetry. When we first designed them in thoughts, we put a photogrammetry task in thoughts. And we also put everything together at a form factor that is IP rated, and it is highly integrated. So let's deep dive into the system capability. For today's webinar, we're going to cover a few sections. First, we're going to talk about the L3 itself, covering the sensor specification. And we're also going to cover the software aspect of the things. That includes our data collection software, data process software, and data application software. Then we're going to talk about some applications and use cases we actually developed for the past 2 to 3 months, along with some users, and share some results we found. And last part of today's webinar, I'm going to talk about some operation tips, as well as recent updates with the M400. First, let's talk about the long-range aspect of this sensor improvement. The typical operation range has been increased to 950 meters. That is the distance from the sensor to the object, at 10% reflectivity. What does that mean? That means you can now fly much higher without losing measurements. It is a different laser wavelength LiDAR. We're now using 1,535 nanometer wavelength LiDAR, and with power output of a maximum of 100 watt, it is still class 1 eye-safe laser. For a typical scenario, for example, I have on the right side, which is 830 meters flight altitude from the aircraft altitude to the bottom of that mine pit. It's about 830 meters. We're still able to collect the data that far away. But for recommended above ground level operations, it is now set to 300 meters to 500 meters. And of course, higher operation elevation, that means larger coverage, that means better efficiency. This is another example of using L3 to measure transmission tower. And these transmission towers are extremely tall. For example, 370 meters on the left side and 260 meters for another transmission tower. By using the power line follow functionality with L3, not only we can capture the data from the power line itself, but also the tower structure. Next aspect is the high accuracy and precision side. For the horizontal and the vertical, we can achieve horizontal being 4 centimeter, vertical being 3 centimeters, 1.2 centimeter point cloud thickness for AGL at 120 meters above ground level operations. And for 300 meters above ground level, we can achieve horizontal being 7.5 centimeter and vertical being 5 centimeter, and accuracy or the thickness of the point cloud is 2 centimeter. And this is a huge improvement from the L2 and making the L3 suitable for topographic survey, digital twin, and overall engineering measurement work. And not only we have increased the accuracy and the precision of the system, we also have increased the laser energy and the laser spot size. So the laser footprint has been reduced. Now it's only about 20% of the L2 laser footprint. And it provides less or smaller laser divergence angle. So this helps better when it comes to penetration or getting more resolution when it comes to smaller or fine detailed surface area. We even have a case study later to show that the L3 system is capable for detecting cracks on the road, for example. And of course, this helps with the vegetation penetration because of the laser footprint. It's smaller. It helps better penetrate through vegetation. And overall, it captures much better in terms of a detailed model because of the lower area of the laser footprint. This is just one example utilizing the L3 for a terrain photo 100 meters above the power line. As you can see, we can reconstruct details of the power line along with the tower. We now also support sampling rate up to 2 megahertz, which is also a great improvement from the L2 and L1 system. It is actually adjustable from 100,000 hertz to 2 megahertz. And by combining with the 1535 nanometer powerful laser, we can now provide options for users either want to create a very detailed point cloud by taking advantage of 2 megahertz scanning rate, or they want to utilize the 100,000 hertz with better penetration, with better penetration due to the higher energy pulse. That is just one example, or two more examples on the right side. For example, for a dam, we like to reconstruct the structure. That way, we use the 2 megahertz scanning sampling rate with an AGL of 50 meters and a speed at 6 meters per second. For the railway site, we have a sampling rate of 2 megahertz to construct the railway in detail with lot of points and increase the point cloud density for scenes or application like these. And we do also provide recommended flight altitude based on the point sampling rate user set. For example, if user set to 2 megahertz, the software will let user know to fly lower than 50 meters. And if user want to fly at a higher altitude, we recommend to use 100 or 350,000 hertz sampling rate. When it comes to returns, L3 has improved on that as well. We now support up to 16 returns with the L3 system. And for the point sampling rate, if we user set to 2 megahertz, they can use up to 4 returns. And if user set to 350,000 hertz or 100,000 hertz, they can utilize that 16 returns. For higher returns, we provide lower rates. For higher rates, we provide lower returns there. And because of the spot size mentioned, combined with a laser spot size mentioned, in combination with the 16 returns, L3 provides much better penetration. I have some results from the case study section to show you. But overall, we suggest to use 350,000 hertz with 16 returns to find a balance between noise level, penetration rate, sampling data, and point cloud density. And this is just one example to show you the vertical profile when we did a scan at a forestry area. And as you can see, the yellow line over there indicates the surface level underneath the canopy. And now we have more examples to show you. This is a data set captured in South Africa for forestry scanning. After the scan, we filter out the vegetation by utilizing the point cloud classification functionality within DJI Terra software. And after we remove the canopy or vegetation above the ground, that reveals the yellow points, which indicates the terrain surface. As you can see, we have a lot of data being classified on the points that indicates good penetration through these dense vegetation using L3 system. Something has also been improved is our scanning method. So right now we support 3 scanning modes. In addition to the linear repetitive scan and a non-repetitive scan, now we're introducing a star-shaped scanning pattern, which finds its balance between the linear scan and non-repetitive scan, and balancing the accuracy output and penetration output. So it is having the same field of view compared to the non-repetitive scan for the L3, which is 80 degrees horizontal, 80 degrees vertical, but also help improve the accuracy. But if you want to make sure to have the best penetration output from the system, we still recommend to use non-repetitive scan. And these are just showing how these scans work in real world. This is directly captured from the DJI Pilot 2 app to show you that scanning pattern, how scanning pattern affects in real world usage. And just one more example to show you the difference between using the linear scanning pattern and star-shaped scanning pattern. Star-shape provides more field of view on the vertical side, and that in that case, it captures more points or data on the facade of the building, just as one example here. Next module I'd like to talk about is the IMU improvements. We have improved the IMU significantly from the L2. In the L3, we can output results with heading accuracy of 0.02 degree and pitch roll accuracy of 0.01 degree. That is 2.5 times better compared to the L2. And we have done more optimization with the L3 system and utilizing advanced algorithm to output lot better results for it to work with its INS system combined with the M400. First, here are some differences. Like first of all, it takes off. You can take off the M400 when it's power on. You don't need to wait for the LiDAR sensor to preheat. This is just like the L2. And in advanced, we also have improved the IMU to have less calibration needed. In the past, when we operate the L1 or L2 system, you need to do the calibration in the mid-flight. Now we have extend that required operation time to reduce number of calibration needed. Right now, if you have a single flight route that is less than 220 seconds, that means from, let me use my laser point. So that means from one turn to the second turn, if it's within 220 seconds, the sensor doesn't need to do calibration. And it actually performs automatic calibration if you plan out a mission within the Pilot 2 app. So you don't need to worry about the calibration at all. The sensor itself does the calibration in the mid-air for the operation set in DJI Pilot app and the DJI Flight Hub 2 app. And because of this, in combination with the M400's 25 meters per second flight speed, this significantly improves the efficiency when compared to the L2 with the M350 system. Of course, the camera is important. Not only we use the camera for colorization, but we also use these cameras for photogrammetry. So L3 system, we're using the Micro Four Third sensor, but with 100 megapixel native resolution. And these two sensors can be used to output 25 megapixel still image by utilizing Quad Bay technology. In results, it outputs 1.2 centimeters of ground sampling distance at a flight height of 120 meters, 400 feet, or at a 300 meters flight height, outputs 3 centimeter ground sampling distance. And it outputs 100 megapixel or 12K photos, stills, or 25 megapixel in 6K. And time interval is amazing with the L3. We can take 2 photos with an interval of 1 second when resolution set to 100 megapixel, or 0.5 seconds for the 25 megapixel. So that helps when it comes to the forward overlaps. And it is extremely doable. Mechanical shutters for both visual cameras, and the shutter rate is 500,000 cycles with guaranteed accuracies. So these cameras are placed to be 170 degree in combined, so it outputs a very large field of view still when taking 2 photos. And in the Pilot software, it is integrated to have user view these 2 photos in live, and we stitch them in the software for operators to view these 2 cameras. So you actually don't see 2 camera views. You actually see one singular combined view of these 2 cameras. But it does capture 2 still images. And we do take advantage of time sync technology. So each photos taken by these 2 cameras have unique and individual camera pose information from the compensation, from the RTK compensation. But for PPK, we also record the camera pose individually for these two cameras. So if you want to do PPK process, you can do that as well. But because of the large field of view of the viewing angle, this significantly improves the efficiency by reducing the side overlaps. Previously, with the L2, you will need to kind of sacrifice the LiDAR overlaps by purposely increase the LiDAR overlaps to make sure sufficient overlaps on the visual sensor side. But for the L3, you can significantly reduce the side overlaps for the visual sensor, but still have sufficient overlaps on the LiDAR side. For users who want to capture LiDAR data and photogrammetry photos from one single mission, this will be something they will be very interested to try out. So overall, about 20% side overlaps for the LiDAR. We have 49% side overlaps for the camera now. And the M400 is the only drone currently to support L3. And there's a reason behind why L3 is currently only compatible with M400. First of all, the L3 weighs about 1.6 kilogram, which is much heavier compared to the L2. When we operate the M350 with L3, that is just making the endurance insufficient or not enough. Doesn't justify on the accuracy side. Secondly, it needs a lot more power compared to the L2. So the M350 simply does not output that much power. M400 is well capable for this sensor by providing enough power. And when getting the L3, we provide a custom mount specifically designed for the L3 system. So users need to swap the existing gimbal mount to have the L3 mounted correctly. And that mount is specifically designed for L3, cannot be used by L2 or P1. This is something needs to be careful. And if you want to use, if you're a user using the L2 and P1 simultaneously, previously with the single downward gimbal mount, you can swap L2 with the P1. That works, but with the L3, just make sure to swap the original single downward gimbal mount for P1 operations because of the payload position has been changed with the new L3 gimbal mount. And that would affect the time sync compensation algorithm. So the camera pose is a little bit off. Anyway, the sensor itself is also IP54 rated, and operation range on the temperature side is -25 degrees to 55 degrees. So under heavy rain, dust, cold, heat environment, our team have done a lot of testing on the L3. Make sure the system is doable under all conditions. And not to mention, it is a gimbalized system or payload, provides a pitch degree from -120 degrees to +60 degrees, yaw from -80 degrees to +80 degrees, and roll from -90 to +60 degrees. So if you want to use the L3 and be creative using it for scanning facade, and you can certainly do that. It is using the same DJI Skyport mount, so it is easy to plug in and use. The field of view has been increased from L2 as well. Now it's 80 degrees by 80 degrees when using Starship scanning mode or the non-repetitive scanning mode. For the transmission line follow, now supports 130 meters from the line to 10 meters from the line. And we do provide recommended settings that is 50 meters to 80 meters above the transmission line. Distribution line, similarly, and we provide recommended settings to be 30 to 50 meters above distribution line scan. And DJI Pilot application, which is built into the remote controller, has a functionality to do the power line follow feature. And is free to use for customers who want to do the power line data capture. The drone is smart enough to follow these power line by itself while capturing LiDAR data. And M400 also supports real-time terrain follow, not to mention, and the real-time terrain follow height now increased to 300 meters with error of 10%. And there's no need, again, for heading calibration at all. This is just one example showing you how that's like. The drone flies by itself. It will detect the power line underneath and follows the power line completely by itself. You just need to measure, make sure the speed is okay, and the system is capturing and accumulating the data normally. We also have a laser rangefinder built into the L3 also, and that has been increased or improved as well. Now the maximum range is to 900 meters, which was 500 meters for the L2. And in the software, because we have a lot more degree of freedoms on the hardware side, we provide some automatic suggested parameters for users. You will find if you set altitudes to certain meters, there will be a recommended sampling frequency prompt show up to advise the users to adjust the sensor settings correspondingly. So for beginners or for users did not have much of experience when it comes to airborne LiDAR system using drone on the drone side, this would help them by preventing them setting parameters that may not make sense based on the use scenario. And this is something new as well. Within the Pilot 2 application, we now provide this point cloud density estimation page. So it would show you the estimated point cloud density based on the area of the swath. If we're talking about overlapped swath area, that's going to be shown under the adjacent flight band center scatter plot with provided values in number of points per square meter. And if we're talking about the center of the swath that has no overlaps, that is going to be highlighted in blue, which shows you the center scatter plot point cloud density. And for the edge of the swath, that shows you in red, which shows you the minimum density scatter plot. So by having option there, you have pretty good understanding or expectation of how many points you're going to have accumulated on the surface. And we have added more functionalities on display side. Now you can have and customize different display mode in Pilot 2 app. You can have LiDAR point cloud on the left, visual on the right, or you can have visual on the left, point of view on the right. So you always keep eye on the flight level when it comes to checking if there's no obstacle during the operation. I know many users love to use that. Or you can use point cloud on the side, FPV on the side also. It is more comprehensive information shown and options available for users to take advantage of viewing the of this during the operation. We also support on-site measurement. So on the right, this is something we have on the Pilot 2 app. As you can see, not only you can view the point cloud model on the remote controller side, you can do some measurements directly on the controller. And because of the controller is diluted the data, the accuracy might not be as good. But this does provide you or user opportunities or options to do emergency mapping and measurements for quickly investigate and have information on the current status on the site. You can do line measurement, polyline measurements, area measurements, and provide a very accurate pinpoint directly by tapping on the remote controller, and that gives you the coordinates of the location. And in addition, we have multiple functionality in terms of the data quality checks. The point cloud density estimation is something we have talked about, for example. And we also have on-site quality checks for IMU system and GNSS data. And we also calculate the trajectory before the data process, which to rapidly assess POS status. And we do evaluate vertical RMM root mean square error after the calculation for accuracy verification. Now, moving to the data processing side, DJI Terra flagship version combined with L3 outputs many deliverables and these deliverables are very practical. First of all, we have point cloud, and because of the Terra 5.1 version supports cluster processing, which is something I'm going to talk about. You can now efficiently process large-scale point cloud data utilizing multiple Terra machines. LiDAR fusion with Gaussian splatting is something also we have introduced in this version of the DJI Terra software, which allows users to utilize the L3 point cloud and to perform Gaussian splatting rendering on top of that model, on top of that L3 point cloud model. We also support PPK and can output ortho photo without aerial triangulation, and automatically classification to generate the ground point data set. And from that data set, we can output digital elevation model and TIM model directly from Terra. So these are the functionality we briefed through. And next part of the webinar, I am going to focus on the software processing end. When it comes to the software, that is really the soul of the solution. You want to make sure under all scenarios, you're having the tool needed to fulfill the needs, to fulfill these scenarios and to capture the data efficiently and get the results you want. So on the flight route design or mission planning phase, we have the DJI Pilot 2 app. For the data collection end, we have Pilot 2 app as well. For the data processing end, we have DJI Terra software. For outputting the LAS point cloud format, and we don't charge L3 user for processing these raw data, and all the functionalities for L3 users when it comes to LiDAR processing side are free to use. We also have DJI Modify software that further clean up the point cloud model by doing advanced classification and output results. By modifying the point cloud capture and process from Terra software, and output a more cleaned version of the deliverable. And of course, FlightHub 2 as our cloud-based platform now supports L3 as well. It is capable to generate real-time point cloud to upload the results to FlightHub 2 for viewing. And of course, you can now do the mission planning directly on the FlightHub 2 side for L3 operations. If you prefer to have a desktop version for mission planning instead of poking on the remote controller, FlightHub 2 is one option there. But let's talk about these software, or specifically on Pilot 2, Terra software, and Modify software, a little bit more in depth. First, let's talk about Pilot 2. So Pilot 2 is our software for mission planning and data acquisition monitoring. So we have many flight routes options for user to use, and that includes the aerial route, which is mapping, oblique route, which is utilizing the gimbal of the L3 system to capture multi-angle shooting on the side of the structure for high precision modeling and reality capture purpose. We also have linear flight route that is designed to capture corridor area missions or scenarios like highways, like a power line, like a river, something like that. We also have power line follow functionality built into Pilot app. They're used for automatically recognized power line within the scene and track these power line and follow these power lines by doing automated flights. This is used for power line inspection use. And of course, on the software end, we also can do manual flight as well. You can use the Pilot app to capture these point clouds by doing a manual flight. Pilot 2 software is also free to use. All the features I'm about to talk about are free to use as well. And that's Pilot, right? Now, Terra software, we support a lot of the new updates and functionalities. So there are a few things I like to talk about today. First of all, the L3 data processing is completely free, no charge, and no license required. Users can just download the Terra software from our website and start importing L3 raw data to get them processed. And we have optimized Terra software in our recent release, version 5.1, to optimize the results for, well, relatively lower spec on the PC end. We now have different power mode options based on your system specification. You can set to balance that, kind of balance the performance or the efficiency and overall system stability. Or you can set to be best the power efficiency one that processes longer but does reduce the power consumption. Or you can set to be best performance mode, just to be optimized for processing focused. If you don't have any task running in the background, for example, this is something you might want to use. Or you can set ultimate performance options, which is optimized for the latest generation of Intel CPUs and the latest operating system, which provides the highest reconstruction efficiency available. So this is something settings you can set within Terra software. And for large-scale data process, just giving out the typical example here. For example, per flight from M400 generates the L3 data about 35 gigabytes. That 14 gigabytes is about raw point cloud data. The rest of them are photos. And that it's about 420 gigabytes for 12 flights per day. This is at 300-meter altitude. For the reconstruction scale, if you set it to be, actually you can now set it to enable the block algorithms to split the entire project based on different block size. This enables computer that may not have a best specification out, but still can handle large-scale project processing by processing one block at a time. So a 64 gigabytes RAM computer now supports L3 point cloud data reconstruction task over 100 square kilometer. One thing to pay attention to is the size. The data, the raw data specifically, generated by L3 is significantly more compared to L2 due to the high sampling rate. So do pay attention there. Make sure you have a sufficient amount of storage when processing the L3 data. But next part, this is still with Terra, we'd like to talk about is the data pose. So that is the position and orientation information for the L3 system. So when you are flying the L3 with the M400 under RTK, you are capturing the post information from the local base station. So if you're using, let's say, a N-trip, or if you're using DRTK3 as a base station, that captures a base station file that will be used as a reference source, right? Within Terra software, you can modify the base station center point to adjust the hair position of the base station to a calibrated position. Oops, sorry. One second. Okay, we're back. Sorry about that. You can adjust the base station center point directly in Terra software if you want to adjust the post information. For the PPK, this is something similar. You can capture the L3 data under the GNSS mode without connecting to RTK, or without enable RTK connection. And later on, you just need to import a base station file that is in the same time frame when you capture the data, and use that to correct the results of the result, and use that data to correct data captured from the L3 system. We support RINEX data, and we support RTCM data. And you can also adjust the center points from this window. I had a customers or users was actually wondering if they can be using the DRTK2 for the L3 operation, and the answer is yes. You can use the DRTK2 system to collect DAT format of the base station data, observation data, and import that DAT file into Terra software for PPK process on the L3 end. Okay. Next feature we have within this Terra software is the flight trajectory clipping. You can now modify and edit the flight trajectory using the flight trajectory clipping features. So if you find, for example, one section of the flight trajectory that wasn't capturing the data normally, or maybe lost the RTK, you can choose to clip that trajectory out away from the process. So after the process, you can it will not show up under the final output. You can also clip out the turning areas or sections to have those points excluded from the final output. This is something available already with the latest version of 5.1 version of Terra. Next we have is region of interest and block settings. So let's talk about region of interest first. So now you can actually set region of interest for Terra to define a boundary and output the point cloud data within the constrained boundary. And for example, if you just one example on the right side, our team draw a boundary or region of interest of a DJI logo, and after the process results, it's only gonna show up the results within the boundary you set. And the next we have is the block. So this is interesting. So you can define different blocks based on the custom block size. So you can define a side length of a block, or you can define based on the memory of each block. So this would separate the entire project into multiple different blocks to get processed one at a time. And of course, for accuracy evaluation, we support ground control points and checkpoints functionality. You may have played with this already within Terra software. You can import known points and define the coordinate system of these imported points to be used as ground control points or checkpoints. After you done processing, under the report, it shows the accuracy results. But if the DJI Terra software, when combining, or should I say, when comparing these known points to the actual data from the L3, if there is a plus or minus 0.6 meters, that's about 60 centimeters in vertical, they won't take the results into the report, because very likely you're having a systematic error there that's causing a gap on the vertical side. But this is something you can do directly, and you can do measurements by utilizing the vertical profile tool on the bottom right corner that screenshot shows you to do the measurement per point there. And in terms of data processing, we have accuracy optimization functionality, which helps improves the swath to swath overlap regions accuracy and help them better matched with each other. And we also have algorithm for point cloud smoothing, which is further reduce the point cloud thickness, which can help improve the overall system outputs for concrete or hard floor regions. Not recommended for area that contains vegetations or small elevation change there. We also have a mode to do self-calibration. So if user experience the L3 or L2 point cloud showing color ghosting or colorization not matching with the intensity values of the point cloud, they can do calibration themselves utilizing the LiDAR self-calibration mode. This is the same as the L2. Okay, more functionalities on the ground point classification end. You can now do classification to remove vegetation or above ground structures. You can also merge different flights into one LAS point cloud data. And for the point cloud visualization, we support RGB, reflectivity, elevation, different echo, classification, and trajectory. That is one new viewing visualization option available. And of course, vertical profile measurement is something you have, just like the previous version of of Terra. Next, we're going to talk about little bit more on the RGB fusion reconstruction side, including the Gaussian splatting part. Very interesting part. Earlier, we have introduced the Gaussian splatting, but that was for photogrammetry process, right? But now we're introducing fusion Gaussian splatting, and this applies to L3 data set. You can now do Gaussian splatting utilizing data or point cloud specifically captured by the L3 and render them. So if you we have options for different qualities, you can set to high, which is renders 1.6K resolution images. We can set to extra high, which uses the 6K resolutions for better visual. And we also have preview there just for quick preview, but outputs lower resolution. And for the format, we support TerraJS, PLY, and 3D tile formats. And this is just one example on the bottom right corner there to show you some results utilizing the L3 point cloud for combined with Gaussian fusion splatting on the visual side. Thin objects, vegetations can be reconstructed with very stunning results. And of course, conventional 2D, 3D models that can be output and utilized DJI Terra software to get deliverable out, including 2D maps and 3D models. So 2D maps, we output the digital orthomosaic map and digital surface model, and we combine the LiDAR and RGB imagery to output these results. So separate from the photogrammetry process, we actually do use LiDAR data to output these deliverables also. Well, in terms of point cloud there. For the 3D model side, we support B3DM format, PLY format, OSGB, S3MD, OBJ, and all these formats available. Not going to go through these in detail. If you're interested, can go through these in our Terra release note documentation. Just one option or example to show you the deliverable. This is 3D mesh model and results. And in addition, we output the digital surface model, digital elevation model, and contour lines. These are similar to the options we have introduced previously. So I'm not going to go through these in detail. Next, I'm going to talk about is the cluster reconstruction. This is something different. We have released the cluster reconstruction capability for Terra a long time ago. Now we're recently making a change here. Now, if you're using a Terra standard version or Terra flagship version, you now have the capability to use cluster computation for free. Great news. So now you can take advantage for using Terra software cluster functionality to have multiple PC working on a project or multiple projects simultaneously. Now you have to make sure the master, we call it master, and the node machines are in the same network to kind of work together. And of course, for the RGB, 2D, 3D outputs and LiDAR point cloud reconstructions and Gaussian splatting, of course, all supported. The Gaussian splatting, RGB and LiDAR and terrain results generate is currently not supported, but the RGB 2D and 3D, as well as the general LiDAR point cloud reconstruction are supported. Just to clarify that. Now, so how does it work, right? So we have a master device, which is master node, which first product or first machine to get activated. And we also have node computers. So the difference between these two is the master device actually contains a directory of the original project, and it will be used to contain the original data. And a node machine contains a temporary data storage for receiving these tasks and get these data processed. So you can define the directory, and for the cluster solution to be worked, you have to make sure the master Terra software and node Terra software are all activated. Okay. So the general access or the general device management is like this. So under the Terra settings preference, you can select cluster device management. And from there, you can view different nodes has been binded to the service and their ID, their current status, CPU, GPU, RAM, and version of the Terra software installed. Also, you have different settings for these nodes as well. You can set to be standard, high performance, and custom. The standard is one node to participate in computation. High performance is you can set to auto enables multiple nodes based on the system capacity, or you can set it to be custom. For the existing cluster customers, they would have their software license automatically upgraded to the DJI Terra flagship. And for all the nodes computer, they would have all the nodes computer license upgraded to DJI Terra standard license. Just to clarify that, if in case there are existing Terra cluster users here. But basic operation is you need to form a cluster group to begin with, and the first added device become the control device or the master node. And you can add multiple nodes in this cluster group. And once you add the device into the group, you can start processing. And while you're processing, you can choose to add more nodes or remove more nodes. If you do remove nodes and that node specifically just happened to be running a task, that task will fail, and that's fine because the master node would redistribute the task to a different available subnodes to run. And this happens all kind of seamlessly. We do provide options or example there on the bottom. So for example, if I have a subnode number 1 to 3 from a cluster machine, after submitting a task A from the node 1, node B or node 2 submitted task B, and node 3 submitted task 3. Now these are all individual tasks, but they will run simultaneously to process. Just one example there. So that is the change on the cluster side. The main difference is the Terra standard version and flagship version both supports cluster reconstruction now. So yeah, cool functionality. Now the next part on the software end, or the last part of the software end I'm going to talk about is the DJI Modify software. This is interesting software that is isolated from DJI Terra software that is used to modify the results and refine the visualization better. So friendly interaction, intelligence algorithm, and rich output. So let's talk about a friendly interaction first. So we now have optimized similarly the Modify software to have, relatively speaking, lower specification PCs still be able to process large-scale data. So for example, 32 gigabytes of RAM with Windows 10 or later NVIDIA graphics card with computation score of 5.0 or higher can now edit LES point cloud data over 120 gigabytes. And we utilize something similar to what we have covered in Terra software, which is the block splitting methods. You now can custom design different block based on the size or set it to be auto. So Terra Modify automatically split the entire large point cloud to multiple blocks for you to do visualization, for you to do edit on it. And once you finish separating these blocks, you can render them individually. For the rendering part, we can display RGB colorization results, elevation by elevation, by reflectivity intensity, by number of returns, and by trajectory display, similar to Terra software. This is one large example, or one large project, for example, and we're changing between different rendering display there. Selection tools we have, this is something also can help efficiently do manual point cloud classification. We have a polygon, rectangle, point selection, brush, and color selection tools. And these tools we have can help you better fine-tune the colorization, or not colorization, the classification results. And we also have intelligent selection tools available for you to utilize. So just want to play one example for the manual selection tool before I jump to the intelligence selection tool here, for example. This is just one functionality to use. So for example, you can use rectangle or brush functionality to manually select different points. And for the intelligence selection tool here, we can actually select quick selections. Let me just show you this screenshot. Oh, okay, looks like it's not willing to play. That's fine. But the quick selection tools allows you to select one section of the point and automatically creates a single class based on the class algorithm. And we also support structural selection as well by using the intelligent point cloud segmentations and a clustering algorithm to quickly select a block of point cloud for the corresponding category. Okay, so the next one is the 3D vertical profile. So for the 3D point vertical profile, something we have done differently this time is we now support 3D rotation cross-section. So you can rotate the results, kind of manipulate the vertical sections you defined under the main point cloud viewer, and do measurements and better visualization there by kind of rotating entire, as you can see on the screen. Yep, it's rotating that selection there for that slice over there. And also you can export the selected cross-section LS file also as well. After you import the checkpoints, you can overlay that to perform accuracy checks also. Next one we have is the smoothing resampling. Now, this is similar to the one we have on the Terra software, but in the modify you can define a region and apply smoothing for a specific area or section. So you don't actually have to process the entire point cloud model just for applying that smoothing algorithm globally. Now you can just define a region and apply smoothing there. So again, smoothing is good when it comes to hard surface, relatively flat surface there. The algorithm does clean up the noise a bit more and reduce the point cloud thickness there. Also, you can select density of adjustment by applying a general downsampling algorithms to reduce the point cloud thickness, either by distance or by percentage. Classification. So something we like to emphasize from this release is we now support machine learning classification algorithm, and currently supports ground, vegetation, buildings, power lines, and electricity, pollens, and also dynamic objects and vehicles. For the surface or the ground classification, we have 3 categories for users to select from, including the flat ground, gentle slope, and steep slope. And the user have more options there to select and find and adjust the auto classification results. Again, if the classification isn't perfect, you can also use the manual point cloud selection tool to modify these selected points to assign them to the correct group. When it comes to the deliverables, supports a 10 grid, digital elevation model, counter lines output. Also, pretty standard there. Something different this time we did is we can now do the real-time tin view and the tin editing. So now if you do, for example, here I have an overlap of the points as well as the tin file. If I modify and delete some points, as you can see, that tin gets modified as well simultaneously, shows up in real time also. So that's something different there. Just another example on the right side there to show you how the adjustment, that is a misclassification there on the top of the pile. If we remove those points there, that does clean up and remodified the tin model there. Okay, so let's summarize what we have talked about on the Terra side. Again, if you want to know more information, please feel free to check out our Terra and modified release notes. But for the Terra, L3 data, completely free for LiDAR point cloud tasks, all the functionalities. And we have added cluster reconstruction for LiDAR point cloud task. Also, in addition, we have the flight trajectory clipping, and flight route accuracy can now overlap, now displayed in the quality reports, and we also support hybrid Gaussian splatting process. Cluster reconstruction is now free for users who have standard and flagship Terra licenses. And there are more functionalities. Something I'm just going to highlight here is Terra software now supports the RTX 50 series, a NVIDIA graphics card, which wasn't the case. Same with the Modify software. Just one highlights there. And for the Modify side, optimized functionality by adding the support to process point cloud data that is larger than 120 gigabytes on a computer, only with 32 gigabytes of RAM. and also supports 50 series Blackwell architecture NVIDIA graphics card. Also supports displaying a flight trajectory information for the point cloud processed from DJI Terra software on Modify. And for Modify and Terra software now supports switching between also graphic and perspective views on point cloud viewing. And you can download these two softwares today and from our official website. Okay, we have covered the software part. The next I would like to talk about are some use cases and real world use of the L3. That includes the large area mapping, long range surveying, railway, dam, L3 versus L2, also the accuracy of the L3 system under 400 feet, which for some regions you can only fly up to 400 feet. So we have done more testing with some partners as well for the past 2 to 3 months. Let's look at the first case study we have done. This is in China, and the area of the flight is, or I'm sorry, the area of the project is about 120 square kilometers. This is for topographic survey. The requirements or the objective is to cover over 100 square kilometer and achieve 3 centimeters of the digital elevation model accuracy. And for the 2D, we need to make sure to achieve 5 centimeter. And we only have 3 days to capture and process every result. So the team have used DJI L3 with M400 system, one M400 system with 8 batteries, 2 DRTK3 for referencing source, and of course DJI Power to power up and charge the battery. The flight parameters set was 300-meter flight altitude, 100,000 hertz or kilohertz for scanning rate, 16 returns for better penetration, 17 meters per second to balancing the point cloud density and efficiency. So 20% side overlaps. And the original flight has been set to be separated to 5 different blocks, and that is 12 flights in total, and about 192 ground control points was captured, and entire coverage is about 120 square kilometer. The team actually got separated into 2 different groups. One group did the work collecting all the ground control points and checkpoints. The other group flew from 7 a.m. to 5 p.m. within 1 day at 5 different locations and conducted 12 different flights. And later on used the DJI Terra cluster software to process the data. And here are the results here. So we're able to utilize 161 checkpoints, known points as checkpoints there, and 2.6 centimeter of a vertical root mean square arrow achieved, and 4.3 centimeters of orthophoto root mean square arrow achieved. The road surface thickness is only about 1 centimeter, and effective flight time is about 7.2 hours. The point cloud processing time took 13 hours to finish the process. So we actually from capturing the data to getting the results processed, that's all within 24 hours, and well achieved within the 3 days given time frame there. This is just another example to show the long range capability of the L3. This is a mining pit in Western Australia, one of the most well-known mining pits for gold in Australia. It's about 4 kilometer wide, long and 2 kilometer wide. So it's about 5.5 square kilometer in terms of area coverage. and the maximum depth is about 650 meters from the surface to the bottom of the pit. The team have done testing using M3E system, which took them 3 days to capture the data. And when they switched to M400 combined with the L2 system, that still took them 3 hours to complete the entire scan with 5 different flights. Their objective was to achieve the vertical accuracy within 10 centimeter. And they want to generate a workflow to be able to capture these data in 1 day. So we tried out the L3 with M400 and set the parameters to be 550 meters at a fixed flight altitude, 100,000 hertz for scanning pattern, single return because there's no vegetation, and max out the speed at 25 meters per second and set overlaps to be 60%. The original challenge for this project was that when using the L2 with the M400, you have to kind of get the altitude set to 150 because you want to make sure the accuracy is within the requirements level. When you fly at 150 meters, that means that is well below the pit depth, right? So that means you have to perform some kind of terrain follow flight. And because of doing terrain follow flight there with the L2, the team was completing the 5 tasks within 3 hours. And not to mention, if we kind of have 5 different flights flown there, that is more battery consumptions. You need to change the battery a lot more. You may need to worry about losing the RTK there. And there is a potential risk for losing the signal because as the drone approaching to the bottom of the pit, you may lose connections because of the challenge maintaining line of sight there for some scenarios. And the pilot may lose attention when you especially flying at that long, 3 hours nonstop there. So when switching to the L3, the team was shocking to find they could complete the entire flight with the L3 just in 15 minutes compared to 3 hours. And that was to cover the entire site at 550 meters fixed altitude and coverage about 5.7 square kilometer. And the team was curious to do another scan just to cover more coverage, and then that was 6.9, almost 7 square kilometers. And that only took 2 flights. That is only 37 minutes. Still way, way shorter compared to L2 combined with the 350 system. And this is because of the high or long range capability of the L3. Now, not only you're capturing the data a lot faster, the amount of the data and to process is significantly less too. When we're comparing between the L2, the L3 generates 23 gigabytes of raw data. The L2, in contrast, generates 44 gigabytes of data. And for the L3, it only took the Terra software 1.5 hours to process. And on the L2 side, it took the Terra software 12 hours and 30 minutes to process there. Significantly improvements when it comes to data processing end. So combine that data process with the data acquisition efficiency improvements, we're able to get the results out within just 2-3 hours. This is crazy to think about. And this is the general quality output from this specific project. So 1 ground control point were used to apply the height transfer, and the other 5 known points there were used to check the accuracy, and we were able to achieve the accuracy underneath the 10 centimeter level and maintain a point thickness of 2 to 4 centimeters and producing enough points with the given density reports outputs. This is just one example showing the distance away from the flight altitude to different area of that pie that pit specifically, and the maximum we reached was like 730 meters. And overall, only took 1 hour to get everything processed. So the total data collection and combined with process time is less than 2 hours. The team find the L3 system is 12 times more efficient compared to the L2 when it comes to this specific scenario. Next one I would like to share is about railway. So the challenge here is to capture a very detailed visual representation of the rail to reconstruct very thin or small objects like T-rail shape on the upper right corner there. So the team was using L3, and because we want to have a high fineness of the point cloud results, we set the scanning rate to be maximum, which is 2 megahertz, and set returns to be single and speed to be low, 6 meters per second, 70% overlaps. And we have executed 2 flight routes, complete the total length of data captured 480 meters, and that only took 6 minutes to capture the data. On the right side, that's just a screen recording of the DJI Pilot 2 app while collecting the data, while utilizing the benefits for having FOV cameras on the right side and LiDAR data capture view on the left side. And the data quality is following. So only took Terra 10 minutes to get the results processed, and the raw data is about 7.7 gigabytes. And overall, the row thickness is less than 1.5 centimeter. And the density we're able to achieve is about 6,800 points per square meter. Lots of data there. And we're able to view the cross section of the trail, of the rail, without any issues, and do further measurements on it. So as you can see from the cross section here, you can clearly see that T-shaped trail there, and you can do further measurements on it. This is another project we have done in France. The objective is to do a reality capture task for this dam structure and to capture as detailed or as high density as possible for this specific structure here. We use the L3 and set the scanning rate again to be maximum, to be 2 megahertz, and utilizing the conventional linear scanning pattern, and set a cross route or oblique missions within within Pilot 2 software, and capture 2 flight routes in total, and completed the data capture within 6 minutes only. Here are the results. We're able to achieve hard surface point cloud thickness within 10 millimeter, and by Terra, we are able to achieve about 6,500 points per square meters with a very, very detailed scans over on the structure. This is not from facade scanning, this is from oblique capture. And here we have more examples showing the data quality or the general thickness of the scan. And the overall point cloud thickness is within 1 centimeter. This one specifically we're showing is 0.6 centimeter. And this one we're showing right now is showing the thickness of 0.4 centimeter. Yeah, and more examples here on the side of the building, on the top of the dam. Overall, the hard surface point thickness is within 1 centimeter. Here is another project we have done in Italy along with a partner, and to complete a L2 versus L3 performance comparison. the team was able to set similar parameters for both L2 and L1 and trying to see the differences there. So the flight height was set to 150 meters, 15 meters per second speed, non-repetitive scanning pattern, and 40% side overlaps. L2 was set to 5 returns. L3 was set to 16 returns. We're trying to compare the penetration results from L2 to L3. Now, for the penetration task, it took 2 hours and 11 minutes because we have to make sure the same flight speed. But overall, 6 points were captured for checking the accuracy. And here are the results. So when we have a look at the cross section after the classification, the ground level points are is a lot more denser on the L3 end. As you can see on the right, that is the penetration on the vertical profile side with 0.1 meters, so 10 centimeter with vertical profile there versus L2. As you can see, there are more data from the L3 end. And if we look at more cross-section areas, compare from the L2 penetration to L3 penetration, you can definitely see that there are more data or points accumulated on the ground surface has been measured and returned back to the sensor. As you can see, if we have a look at the ground classified points there and results, you can see much more points on the L3 end. Overall, L2 from 22 points to 63 points per square meter versus L3, which is 78 points to 80 points per square meters. Now let's have a look at the efficiency comparison here. So the task was actually filmed, and interesting part is upper left corner there, I should say northwest region of this scan was actually having a challenge there because there's there's a giant elevation dip from where the team took off the L3. But the result is due to the long range of the L3, L3 is able to capture that data without problem. And this elevation drop is 550 meters. And when we look at the noise level here, the output L3 generates about 1 to 3 centimeter level on the hard surface from the given parameters, flight parameters here. And when it comes to the accuracy from the 6 checkpoints applied, and general accuracy for the flight is about 3.77 centimeter from Italy team here. More results here, and the team was actually be able to capture another flight and just try out the 2 megahertz scanning mode for a flight here. And they were flying this at 110 meters, which is not recommended, but good to try and see the results here. And the amount of points and the density is stunning. You can really see many details when it comes to the edge of the building, little corner, alley, and when we set the vertical profile to measure, the thickness is actually in millimeter level on the hard flat surface end. Really great results. This is another case study we have done with a partner in Kansas City. They helped to evaluate the L3 accuracy and precision under 400 feet above ground level, because many regions in the world can only fly and operate UAV at 400 meters ceiling level. So it will be interesting to check out the L3 accuracy performance under 400 feet or at 400 feet level. So we know what kind of systematic accuracy we are expecting from the L3 system. So the team was actually using the PPK methods and utilizing a base station from Robodot and collected 30 checkpoints at an area about 40 acres, all on the hard surface level, and using the ASPRS standard to evaluate the results of the L3, accuracy results from the L3. It is very challenging from the team side because L3 is a very accurate system, so you have to make sure your checkpoint is accurate enough in order to reflect the accuracy error of the L3. But overall, the team was actually set 12 different flights at a different flight altitude at 200 feet, 300 feet, and 400 feet. And each altitude, they set different sampling rate just to want to see how different sampling rate there and different return modes would affect the overall accuracy performance. Overall, this is the results. So we're able to achieve vertical root mean square error within 1.3 centimeters within all 12 flights. Natively, these point cloud data were natively outputted from DJI Terra. No further filter applied, no further post-processing applied. This is the direct results outputted from DJI Terra. And we're able to achieve vertical accuracy of 1.3 centimeters, all within 400 feet flight altitude. If you're interested, you can check out the more detailed white paper Vertical Aspect team have conducted under their website, and we'll be hosting a webinar later this year to go through these results and the methodology they used. So please stay tuned and subscribe the DJI webinar. The next project we have is happening in, I should say happening, yeah, because it's still happening, in Quebec, Canada. This specific project was trying to utilize the L3 on the power line scan there. A previous challenge with L2 system was that we have to make sure all the leaves fall off from the tree so we can start measurement, because these leaf is giving a hard time for L2 system because they're very dense vegetations covering the power line. So it's kind of hard to capture the power line from the L2 there. So the team was trying to see how L3 system could change that. So setting up the parameters and at a different altitude, which is 100 meters and 8 meters per second, set overlaps to 50%, flight paths to be 2 lines, corridor mission, and scanning angle to be star-shaped scanning. Completed the flight within 10 meters and set the flight altitude, flight frequency to be 350,000 hertz. The result is utilizing the L3 was able to provide required penetration rate to extract the required features from the power line sections, even with the full leaf on. This was able to allow the team to do operations without to wait throughout a certain time of the year. Again, we are having a webinar this month on 18th. Grant from our team, he will be providing or hosting a webinar to go through more detailed with Cancel and SEMA Plus, the client, to go through more information on what they found using L3 for this specific application. So please feel free to scan this QR code to register this webinar. Okay, so these are the use cases of L3. Now I do have some operation tips because the system has a lot more options for users to select now. First of all, the 2 megahertz scanning options right now. We do actually recommend users to fly within 50 meters flight altitude. Actually, inside our software, they would if they exceed 50 meters, it would get warning there. And to be noted that the 2 megahertz scanning frequency does output significantly a lot of data. So for 6 minutes flight, it generates 7.2 gigabytes. And for 1.4 kilometer long route flight, within 7 minutes, it actually collects about 32 gigabytes of the data. So the raw data, there's a lot of data to capture. So I would say, based on the use scenario, if you want better penetration, the 2 megahertz scanning sampling rate, it might not be the perfect settings for you, because when we have more points, that means the laser energy has been distributed more. So that means a single laser pulse have less energy. So in this case, we recommend consider using 100,000 hertz or 350 kilohertz for better penetration results. Overall, if you want to capture detailed scans for a very small scene, for reality capture purpose, 2 megahertz at 50 meters altitude or lower would be something you may want to consider using. But if you want to do topographic survey or better penetration through vegetation, you may want to consider using 350 kilohertz or 100 kilohertz frequency rate here. Another example here to show you why exactly it generates so much data. That's because of the LiDAR point cloud density here. Overlaps, that's another thing to keep in mind. When you're operating at a location that has elevation drop scenario, or you may want to consider if your overlaps is sufficient or not. So for example, on this specific case here, upper right corner, that shows you that the overlaps is insufficient because of the flight altitude was designed, the HEL altitude was designed at lower ground altitude. When it flies to the region that has elevation increased, that overlaps suddenly is insufficient. So you have to think about that when you're doing a scan for a region that has dramatic elevation changes. So for this one specifically, you can choose to increase overlaps ratio, or you can choose to raise the flight altitude, or you can do both. That increase the efficiency as well. Next, I could talk about is the overlaps. So when we're doing the corridor scan, so for like power line, railway, highway, those civilization projects, when we're talking about these projects and utilizing the corridor missions type, we want to make sure to capture at least 2 flight routes for the L3. That means you need to make sure there are 2 swaths captured. And between 2 swaths, there's overlaps, because a single swath would have a slightly lower density on the edge of the swath, and accuracy-wise as well. But having 2 swaths with some overlaps in the middle, that helps the software algorithm to improve the accuracy output and result, and improve the density overall for the center area. Okay. Now the next part is the facade scanning. For the L3, due to the long range of the L3, it's actually not recommended to do the gimbal 0-degree facade scanning, because it would shoot the laser to near infinite and capture a lot of noise. So for a scenario, we want to do or use L3 for facade scanning to output detailed model, we actually recommend to use the oblique mission. So flying two different flight routes, but with the gimbal pitched to a certain angle to capture the data. That way you constrain the laser range by heading to the ground, not to infinite. So here we have an example on the right side to show you not to not to do that. This will accumulate lots of noise and unnecessary data there. Next tip we have is related to the star-shaped scanning mode. So this is the new scanning mode we introduced with the L3 sensor, which is great and awesome because it balances the accuracy and penetration. However, we need to make sure to understand, because of how these points get, because of how the laser module is moving inside the LiDAR for this specific scanning mode, there is a chance it would create some gaps or small black holes or sketch lines there. If you don't want to have these points distributed like unevenly like this, consider use the conventional linear scan method, which would provide the distribution of the lines more evenly on the scanning on the site there. Okay, so that's the operation tips there. And that kind of concludes the L3, but I do have more information on the M400 side because we have released the M400 updates for the L3 along with the L3 also. And first of all, some features on the M400 side is we now support, well, we did support a ship-based takeoff. In case you don't know, you can take off this from the ship, and we do provide a landing marker available on our website for you to download. It's a PDF file for you to print out, and you can print out a target at a size of 3 × 3 meters, and you can lay that marker on the ship. And when you try to land on the ship, because the vehicle is a moving object, right? So we use the obstacle sensing to detect the marker and for precision landing. Now, with the new firmware, we now support the marker-based landing. So I have a video to show you how that works. Basically, when you're hovering at 100 meters or below, when you point the H30 cameras to the marker, it would start detecting the marker. Once you detect it, you can press the C1 customizable button on the left, on the back of the, or shall I say, on the bottom of the remote controller, and it would start the automatic landing sequence automatically. So yeah, that is a cool feature to have while the boat is moving, and get the drone landed on the boat there. Second update is the relay functionality. So we now support using the M4D, M4TD drone, and the DRTK3 base station as a relay for the M400 drone. And you can now use DRTK3 or the docked version or non-docked version of M4 enterprise drones for them as a relay to use the M400 as a worker drone. The only combination currently is not working is to use the M400 as a relay for the M4D or M4TD drone. That is just one update there. Next we have is the charging case power adjustment. You can now change the power input. Oops. You can now change the power input of the charging case. Previously, it was default to 2,100 watts, but if you're using like a RV or an inverter, doesn't output that much of a power, you can now set lower power output mode, so it takes less stress, I guess, from the RV system or external battery source. This is something you can change inside the Pilot 2 settings. And for the split screen updates, remember we covered from the L3 section. Now with the H30T, you can also take advantage of this by setting infrared plus zoom, or wide angle plus FPV, or zoom plus FPV as well, similar to the L3. And we now support the quick gimbal auto spin to aircraft heading. So what does this mean is you can now one tap to have the aircraft heading synchronized to where your camera is looking at. So just tap on these options, the aircraft heading will automatically adjust to where you're looking at. And now we support L2 plus H30T to work simultaneously for the dual gimbal power line follow feature. This is a feature a lot of people are asking. Now you can use L2 with H30T simultaneously by using a dual gimbal mount, and have L2 to perform power line follow feature, and have H30T to capture corridor inspection photos. We also have done changes here on the obstacle avoidance status, because the M400 is equipping with a lot of different sensors, LiDAR sensors, fisheye obstacle avoidance sensors, millimeter wave radar. Like a lot of these sensors, you kind of have to know the current operating status while you're operating these. So we provide a guideline on the right side to kind of show you what that means if you run into like these warnings or warnings or error. Okay. So for example, if the marker icon in the center is white, that means operation normally on the LiDAR side. If it's red, that means something on the vision sensoring is either disabled or not functioning properly. Okay, I think that's everything about today's webinar. Let me look. Okay, I have 6 more minutes. I'm willing to answer any questions you may have. Okay, looks like Grant and Michael have been answering your questions. Thank you, Grant and Michael. Let me kind of turn on my camera, see if this works. And if you have more questions, please feel free to leave them. And for the next few minutes, I can help answer these questions you may have. Otherwise, yeah, thank you for your time. Very exciting product, in my opinion. Okay. Many people are asking about recording. Yes, we will push the recording of this webinar out to YouTube. So you should be able to find the material on YouTube soon. Okay, so let me see. Yeah, it looks like Grant have been answering a lot of questions. Thank you, Grant. Okay, I'm getting some questions now. So what is the resolution of the L3 camera? So natively, the L3 camera, it has 2 cameras. Natively, the resolution is 100 megapixel native, and it does support 25 megapixel as options for output. A lot of people are asking about the parameters on the different scenarios. Later on in our L3 manual, we do provide settings based on the use scenarios, and Later on, we'll be providing something similar to the L2 white paper as a guideline for users for to use L3 with. Let's see. Is there like a difficulty using the sensor due to the humidity in Amazon rainforest? What about the case of the fog? That is a good question. So for clients in South America, you may need to kind of think about the humidity side. The L3 sensor is indeed IP rated. So our team have done testing under humid situations and have no issues. Will I be able to use the L3 with the M400 RTK? No, sir, you cannot use the L3 with the M400. L3 is currently only compatible with the M400 system. And the reason I kind of explained was the M300/350 is not having sufficient payload capacity to carry the L3, which is a lot heavier than the L2, nor providing enough power for the L3. Okay. So for the pricing, depends on your region. You can find pricing on the website of your local dealers. And generally speaking, our pricing is pretty transparent to public. What is the suggested flight speed for topo through vegetation? So the recommended flight speed for topographic survey through vegetation, you kind of need to consider the well, I usually like to work on the way backwards. Like I would like to know what kind of achievements I would like to get from the LiDAR data. For example, per square meter, I would like to have 20 points or 30 points from the ground level. That way, I kind of work backwards. Like let's say to be safe, I multiply the safety factor about 10. So for example, if I have 100 points, I would expect 10 points get distributed on the surface, on the ground, sorry, not on the surface. 100 points on the surface, roughly 10 points on the ground. Of course, that's going to due to the vegetation density, of course, that's going to affect the penetration rate. But usually I like to work that way. So when I plan out a mission, I check the density output to make sure I have sufficient estimated amount of surface, estimated the points distributed amount of the surface per square meter, for example. That way, I plan out my mission that way. Of course, the flight speed would relate to the point cloud density as well, because the slower you fly, more points you're going to get accumulated. I like to find that balance there, because you don't actually want to collect too many points you don't need, because that reduces the efficiency a lot, right? So it's all about picking up that balance there. You have spoken about the power transmission photo capability for the M400 with L3. Is the Terra electricity version required? We no longer have Terra electricity version. Now we only have Terra standard and the Terra flagship versions. The transmission power line following capability, that is not on Terra. That is actually on the Pilot 2 software. So it's the mobile software on the remote controller. And that functionality is built into the controller for free. So you don't actually need to pay anything to use Pilot 2. Anything when it comes to Pilot 2 functionality, we don't charge anything. Nor, I guess, for the Terra processing end when it comes to point cloud related. since there's a greater amount of points being collected, what is the minimum size of SD card you recommend to use for data collection? Great point. We don't use SD card for the L3 anymore. We actually use CF Express Type B memory card. And when you purchase the L3, it came with 2 storage cards. Yeah, so because of just more data to be captured now. So we don't use micro SD card anymore. We use the CF card now. Let me see if there's more questions. Okay, looks like that's every question. Thank you all again for your time, and I'll see you in the next webinar. Thank you all.